So a pointer to the page table is stored with the other register values, just like the instruction pointer, in the process control block, right? Remember the PCB of each process. So most CPUs, they support large page table, like multiple hundreds of entries. And for such machines, the use of fast registers is just not possible and not feasible because registers are, yes, they're fast, but they are small in capacity. And so the page table is then kept in main memory. And so for every data or instruction access, we will need two memory accesses in reality. So one for the page table, because we have to know in what frame we are supposed to find that data or instruction, right? So once we look at the page table and we retrieve the frame number, then we have to execute a second memory access to retrieve that the actual data and the instruction from memory. So again, this will slow us down because we're doing two memory accesses. Now, to solve this problem, we can use a special fast lookup hardware cache that is called Translation Look-Aside Buffer, or TLB. It's also sometimes called associative memory. So it's a fast access type of cache that will enable us to have a fast retrieval of the frame number from the page table. So TLBs, it's true that they are fast, but again, they're small in capacity. They can take 64 to 1,024 entries, and then therefore the TLB can used with page tables in the following manner. So when a logical address space, when a logical address is generated by the CPU, then the memory management unit will first check the TLB. So with the TLB, since it's small, we're just going to keep a subset of the page table entries. We cannot put all the entries of the page table because we said the TLB is small. Therefore, we're just going to keep a subset of the page table. And then once a CPU generates an address, then the memory management unit will first check TLB because it's fast access. And then there will be two possible scenarios, right? Either the address is there or it's not there, because remember, the TLB has just one subset. It just has a small subset of the page table, not the entire entries. And so the first possible scenario is that the page number was actually found in the TLB itself, and we call this a hit. Okay, once we find the page number, then we immediately retrieve the frame number and we directly access that data or instruction that we need in the physical memory. Now the problem happens if we have a miss, meaning we did not find that page number in the TLB. Okay, then in that case we do have to do one access to the memory to get the frame from the entire page table that again it's saved in memory, and only a subset of it is in the TLB. And since we didn't find our page number in that subset, we have to go to the page, the entire page table that again it's in the memory to retrieve that page number and the corresponding frame number. Then we go ahead and access memory again to retrieve that data or instruction. So in the case of a hit, we only have one access to the physical memory to get the data or instruction. But in the case of a miss, we access memory twice. First to access the page table to get the frame, and second to get the data or the instruction. And so there is something called the principle of locality. And it says that the location accessed recently by a process are most likely going to be accessed again in the future than the locations that were accessed back distant in the past. So therefore, based on this principle, the TLB will update and replace the current entries with the least with the most recently used entry. So when we had a miss, and then for instance we were looking for page number 4 and we had a miss, we didn't find it in the TLB, but then we accessed the page table in memory and we found that it belongs to frame number 10. Then what the TLB will do also is to update, so it will replace one of the entries that are not recently used by this one that was recently used, and it will write page number 4 and frame number 10. This way, when the process will again try to access page 4 in the future, it will find it already there. So some entries can be wired down, meaning they will never be replaced and they will stay permanently in the TLB. Things like some key kernel code that's really crucial, and we want fast access to it and fast retrieval, and therefore we can wire those down in the TLB and never replace them. So here we will define something called the hit ratio. So it's the percentage of time that a page number is actually found in the TLB, which means a hit. So if we say we have a hit ratio of 80%, this means that 80% of the time we always find that desired page number in the TLB. And so suppose we need 10 nanoseconds to access memory. So therefore, in the case of a hit, which is 80% of the time, we only going to need one access to memory because it's the page table is already in the TLB. So we're going to retrieve the frame number and we're going to access memory just once to get the data or the instruction. Therefore, in the case of the hit, we're going to need just 10 nanoseconds. Versus in the case of a miss, which is the other 20%, right, 1 minus 0.8, we are going to access the memory twice. So 10 nanoseconds times 2, so the first access is to get the frame number from the page table itself, and the second access is to retrieve the data or instruction. So this is the effective access time, okay? So realistically, if we consider a hit ratio of 99%, then the effective access time will be actually 10.1 nanoseconds instead of 10. And that slowdown, 1% slowdown, is due to the fact that sometimes we do have a miss and the page number entry is not in the TLB. So to ensure protection, we can use a bit that's called the valid invalid bit, and if it's set to 1, then this means that that page is actually a legal page for that process. It does belong to its own logical address space, versus if it's not valid, then it's considered an illegal access because it does not belong to its own logical address space. And so sometimes if the program size is not a multiple of the page size, then what happens is a portion of the page size will go to internal fragmentation. Okay, remember, internal fragmentation is that space that is already allocated to a process, but it's unused. Okay, so to make sure that we protect this portion, that from any access from this process, we need to compare the address to the program size itself. So if the address is beyond the program size, we're going to consider it as illegal. And so if the page size is 512 words and the program size is 1536 words, then which address is illegal? So the address that's illegal is actually 1536, because we're going to always start from 0 to 1535. So anything beyond that is considered illegal. And so if we have the page size again of 512 words and the program size of 1536 words, then how many words are lost for internal fragmentation? So in this case, the program size is a multiplier of the page size. Therefore, we're not going to lose any words for internal fragmentation. Now, in this scenario, the program size is not a multiplier of the page size, and so we're gonna end up with one entire page that we only going to use one word of it. And so if the page size is 512 words, we're only going to use one and lose 511 words for internal fragmentation. So lastly, to do the translation of the logical address to the physical address, for instance, if we want to translate this logical address into a physical address, then we divide it by the page size. If we assume that the page size in this example is 512 words, then we going to have the page number 9 and the offset 0. So we have to go to look in our page table for the entry 9, and then we will find the corresponding frame number, which is in this case frame number 4, and therefore the physical address will be the frame number times again the frame size plus the offset, which was 0. So this will give you this physical address, and you can do the same for this physical address as a practice.